All right, guys. All right. Today we are going over in this video, we're going over question 4 on the 2025 AP Chem exam from May 6th. Okay. And again, I'm just prefacing this. My students haven't taken, the West Springfield High School students haven't taken the AP Chemistry exam yet. We're taking it on the second date, May 21st. So hopefully my students are using this as a chance to review and prepare for their exam. If you've already taken it, hopefully you're getting the same answers I'm getting, or maybe I'm incorrect and you're getting them right. But I think I'm getting them correct. Let's see. All right. So this is question 4. So now we're on the shorter form questions. So, questions 1, 2, and 3, they were all worth 10 points apiece. So a total of 30 points. So now we only have 16 more points to go in this test. And it's 4 points each question. And they made it easy for us because question 4, question 5, question 6, question 7 all have 4 prompts apiece. So we know each one is just worth 1 point, okay? So thinking about, cutting and running, right? Remember we read down. So if you need the answer from part B to answer part C, but you don't know how to get part B, maybe make something up and use it correctly in part C and hopefully get your points, that kind of thing. Okay, but remember, these questions shouldn't take nearly as long as question 1, question 2, and question 3, okay? Boom, 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 we're talking about like 10 minutes a question, okay? So here we got a diagram of methanol and formaldehyde, the first question is a hybridization question of the carbon atom in the formaldehyde molecule. So in this one. So that's easy. That should be a quick one, and we don't have to justify. So we should just write sp2 and we're done with it, right? So we have 1, 2, 3 electron domains around the carbon. Anytime you have 3 domains, it's sp2. That's it, okay? So let's do some other ones. Like if they ask this carbon, we have 1, 2, 3, 4 domains, so that would be sp3. If they asked about the oxygen, that has 4 domains, so that would be sp3. This oxygen would be sp2 because it has only 3 domains versus 4 domains over here, okay? So part A, we have 3 electron domains around the carbon, so it's sp2, the hybridization, okay? Then it says draw basically a hydrogen bond between the particles here. So remember, one of the things have to come off of one of our FON bonds, right? So one of the parts of the interaction have to be from, either the positive dipole or the negative dipole of hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, or hydrogen bonded to fluorine, depending on what you have. So here, our interaction has to be between, something between here and it has to be between opposite poles. So the easiest one, the one they have lined up for us, is the negative dipole of formaldehyde interacting with the positive dipole of this OH bond, right? So that would be a very strong interaction right there, a hydrogen bond. Okay, so that's where I drew it. You could, I guess you could draw it weirdly and draw it all the way from here to there, okay? But if you drew it from here to that H, that's not gonna be the right answer, right? It can't be interaction with an H coming off a carbon, right? There's not a very strong positive dipole on this hydrogen, but there is a very strong positive dipole on that hydrogen. Okay, so you got to be careful. All right, so bad drawing, but that's where I had it. I think I have the actual paper, so that's where I drew mine. Okay, but there would be you could go from here to there, but that's what they're looking for. Okay. All right. So the next question, so they give us, melting point, boiling point, and enthalpy, delta H of vaporization. Notice the methanol has a lower melting point, but it has a higher boiling point. It has a higher heat of vaporization. It means it has stronger IMFs, and that's probably because, methanol can have hydrogen bonding between its molecules, but formaldehyde can only have dipole-dipole interactions, that kind of thing. So just things to think about. That's not what they ask here, but So part C is an odd question, but it's an easy question. But I think kids can get confused by all the information that they're given. It's just where propose a temperature where this mixture could be cooled so that both are in the liquid state. So it's got to be somewhere. It's got to be between both melting points and both boiling points of the substances. So it's got to be above 182, but below 254, right? So any temperature in that range would work. What did I say? Whoops, where did I have it? Oh, let's go back up here. I said 200 Kelvin, all right? And notice it was in Kelvin, so if you accidentally said degrees Celsius, that would be wrong. But I'm sure their answer key is going to say, anything between these temperatures. So that would work, okay? And then the next one is just, hey, how much energy is going to be released when this many grams condenses? So they could ask the same kind of question: how much energy is required to vaporize this many grams? And we don't have to worry about heating curves or anything like that because we're at the boiling point. And remember, the boiling point and the point of condensation are the same point. So it's not like we have to do Q equals MCAT to cool it down to the point of condensation and then do the delta H of vaporization to see how much energy is released as it condenses. We don't have to worry about that. All this is basic dimensional analysis. So we would take our grams of methanol, they gave us the molar mass, divide by the molar mass, that'll give us moles, and then multiply it by the molar heat of vaporization. Remember, the molar heat of vaporization is also the molar heat of condensation. It's the same value, it's just energy absorbed if it was vaporizing, energy released if it was condensing, okay? And so it would look like this. So we would take our grams divided by the molar mass, get moles, moles times the molar heat of vaporization would get that. So that much energy removed. Now, since that's what the question asked, you don't need the negative sign. But if it said what would be the energy change as it condenses, then you would need the negative sign. So maybe that's how they beef up your test on May 21st for the West Springfield students. Maybe they don't remind you that when you condense, you're releasing energy. Maybe you have to show that with the algebraic sign of a negative energy value, but you don't need it in this one, all right? Okay. And that was question 4. All right, so again, shorter, so we're good. And, why not, let's do question 5 as well, all right? We got time. Let's do question 5 on this video, all right? We're gonna do another one, all right? So question 5, here we go. So we have these two diagrams. The quick thing to notice is the only difference between these two molecules is this has silicon here, whereas that has carbon at its like central location there, okay? But they have an OH group, and they have methyl groups coming off of the silicon, and they have methyl groups coming off of the carbon, and so it's basically identical molecules except for carbon versus silicon in that location. Different molar masses, the main reason is because silicon, has more mass than carbon. And different boiling points, okay? So, this has the higher boiling point, so stronger IMFs, okay? All right. So, based on Vesper theory, predict the geometry of the silicon atom here. So, again, remember, in question 4, it asked us hybridization, and question 5 is asking us shape. So, again, it's about the electron domains, but shape is about, now it says geometry, so shape and geometry are a little bit different. If you have, one lone pair and 3 bonds, the shape is trigonal pyramidal, but the geometry could be called tetrahedral anytime you have 4 domains. So the geometry for 4 domains around your central atom is always tetrahedral. And the shape would be tetrahedral if they're all bonding domains. And so the shape and the geometry are the same for the silicon. So the answer is tetrahedral. You got 4 domains, 4 bonding domains, that's tetrahedral, okay? So let's see if we got, tetrahedral. And we don't have to justify, so, right? If they don't say explain, don't explain. You're wasting your time, okay? Tetrahedral. And if you say tetrahedral and then you say something that's incorrect about tetrahedral, then you get it wrong, okay? So remember, hey, tetrahedral, right? Look at my answer for for A, sp2. That's it. All right. So here we go. All right. So tetrahedral. All right. The student claims that the compound Y has a higher boiling point than that of compound X because compound Y has stronger London dispersion forces. Do you agree or disagree? Again, we had a smart student taking this test. We agree. We agree with that student on this one. And it's because they both have hydrogen bonding capabilities and they both have the same amount of hydrogen bonding capabilities, right? They only have one OH group, right? Maybe if this one had an OH group here and an OH group here, then it would have more opportunities for hydrogen bonding, and hydrogen bonding would be the dominant factor compared to this that only has one site for it. But one site for hydrogen bonding, and the rest is just based on, weak dipole-dipole interactions because the bonds aren't very polar, and then London dispersion forces. So the main difference, because they both have about equal hydrogen bonding, the main difference would be the London dispersion forces. And remember, the more electrons you have, the stronger the London dispersion. And silicon has more electrons than carbon, and that's the difference. This molecule has more electrons than this molecule, and because of it, it has stronger LDFs, and that is the big difference between this boiling point and that boiling point. Okay, so we agree. The only difference in the molecules, I should say, the only difference between the molecules is one carbon and one silicon. Okay, one has carbon and one has. I gotta edit my stuff better. One has carbon in the middle and one has silicon in the middle. Both compounds would have similar hydrogen bonding capabilities because they only have one OH. But since silicon has more total electrons, that gives it stronger LDF forces. Okay. All right. Part C, equal moles of the two compounds is heated. When the mixture reaches 82 degrees, which compound will have the higher vapor pressure? Okay. Well, notice 82 is the boiling point of this. And so that would be one way to answer the question. But what you really need to remember is when you have two liquids at any temperature, as long as they're at the same temperature, the one with the higher vapor pressure has weaker IMFs. The one with the lower vapor pressure has stronger IMFs because vapor pressure is based on the amount of particles that were able to become vapor, to escape to break the bonds of the IMFs and go to the gas phase. So higher vapor pressure means more gas particles, more particles able to overcome their IMFs, therefore a higher vapor pressure. So the higher the vapor pressure, the weaker are the IMFs. So Part C is really just asking you which of these compounds have weaker IMFs. Well, we already did it, right? We already came to that conclusion in our minds already. So it would be compound X would be the compound that has the higher vapor pressure. And the reason is because it has weaker IMFs. It has weaker London dispersion forces. So you could say it that way. Now, the other way is understanding the definition of boiling point. What boiling point means is the temperature where the vapor pressure equals the atmospheric pressure. So if you reach the boiling point of a liquid, you know the vapor pressure is equal to the pressure of the atmosphere. And if you haven't reached it yet, then the vapor pressure is not at the pressure of the atmosphere yet. It has to be less, right? You heat up a liquid, its vapor pressure increases until that vapor pressure is equal to the atmospheric pressure, and that's when boiling occurs. Okay, so you could have, maybe mentioned that in your explanation. Okay, so compound X, because it has weaker IMFs, therefore at the same temperature, more X will vaporize. More vapor particles equals higher vapor pressure. Okay, the other way to think about it is at the boiling point, vapor pressure equals atmospheric pressure. 82 degrees Celsius is the boiling point of X, but not Y. All right. All right, so, and then in the last part of the question, so when I first did my answers, I totally skipped over part D for number 5. It didn't register to me. I went right to number 6. And then when I was coming back and double checking, I was reading this and I was like, I don't remember working out this problem. And I was like, oh my God, I didn't. So, make sure you do all the questions. And this one's an easy one. This is just an ideal gas law one. And the only thing you need to really remember is you got to be in Kelvin, right? So you got to add 273 to this and then solve for N, solve for moles in the ideal gas law. So We're doing PV equals nRT, so N equals PV over RT. Our pressure was 2.3 atmospheres. Our volume was 12.5 liters. The R value we use for atmospheres is 0.08206. It's on your formula sheet. If you need a reminder, let's go check it out. Whoops. Let's check out it where it is on the formula sheet just to be sure. Here we go, 0.08206 atmospheres, right? Okay. And then, 198 plus 273 for your Kelvin temperature. So you do your math and you get around to 3 sig figs, 0.744 moles. All right. All right, so that's question 4 and 5. We'll come back for 6 and 7 in the next video. Smash the subscribe button. Smash it.